Welcome to part 3 of my boost converter flashlight project. Today I'm going to be covering how to use OrCad to simulate the design and just kind of the basics of using OrCad. So first things first, I guess, if you don't have OrCad, you're going to need to download that. And in order to get it, just go to Google and type in like OrCad, search for OrCad. And it'll pop you to like this, and just click on probably this. It's not that hard to find. They're pretty good about it. You can read through all this information, or actually probably a better way to do it would be OrCad downloads. Yeah, free trial. You can go through there to get to it. But basically, when you download that, you're going to want to install it, and it'll give you something along these lines. It'll be look for cadence release 17.2. Come in here, and we're looking for OrCad Capture CIS Lite. Click on that thing. And I have this just running on a laptop, so it does take a little while to open, but it's actually, even on a good desktop, it takes a while to open, so don't panic. Okay, and this is the start page that pops up by default, and it's pretty handy, I think. It's the way I usually start new projects or things like that. So I just click on this new project. It's going to pop open this dialog. Today, I'm going to give it a name. We'll just go boosted flashlight. And several of these options work. I think schematic would work, but just leave it on PSpice analog, and then pick a good location. I'm just going to throw it in. I made a temp directory here, so I'm just going to click on that. And that's it. Click OK. Oh, and this allows you to tack on existing projects. So that's going to give you like part libraries, things like that. Don't worry about it for now. Select empty OPJ. I'll show you how to get the things we're going to need for this. So click OK. And just give it a little bit of time, and it should. Yeah, it's going to open that project for us. So now it's created, and you can go ahead and click this button to save. I know every time I open a new piece of software, it's really intimidating looking at all the icons and options. You know, each one of these has a bunch to do, and even on OrCad, another complication it has is depending on what your active window is, some of these options are going to be grayed out and not available. So, but this is the project. As you're following me along, I like to use a certain flow or kind of place things in a certain way that makes it easier for me. So first thing I like to do is take this tree viewer and I put it on the left. So to do that, click on the tab and then right click it and go to dock to left. You don't have to do this, I just think it makes things easier. So to get to our first schematic page, notice how it's got schematic 1 created for us by default. Open that up, and then page 1 of schematic 1, go ahead and double click to open page 1. I've messed with my settings, and so I have a yellow background. I get bored of staring at white all the time, so I changed that to yellow. Hopefully that's not annoying, but you can do that, I think, by going to options and preferences. Yeah, and here you can change background or whatever you would like it to be. You can do all that, but I leave it as yellow. So, all right. If you remember, let's go here. We're going to be building this boost circuit and trying to simulate it today. And I'm going to try and move quicker because I know these videos have been getting pretty long. But basically, we're going to need a voltage source, a 3-volt voltage source, an inductor, an N-channel MOSFET, a diode, and a capacitor to build the bare bones of the boost circuit. And then all this stuff out on the right is just our load. I'm not going to be putting in LEDs today. I'm just going to simulate it with a simple resistor. So let's go back to our schematic, and let's start putting some of those components down. There's several different ways to place components on your schematic. Probably the easiest way is what I'm going to show you first, which is using these pick menus up here. So if you go to place, which makes sense, I want to place a component, then PSpice components, and here you've got your basics. So you've got capacitors, diodes, inductors, resistors. First thing I'm going to place is the voltage source, that 3-volt source. So that's down on the source tab, and just follow the categories. We got voltage sources, and I want a DC since we're simulating a battery. So I'm just going to place that anywhere by left clicking. Now if I keep clicking, it's going to see how it's still got a new voltage source on my cursor. If I keep clicking, they'll keep populating, but I don't want that. So to get out of that, you can either right click and hit end mode, or it also tells you can just hit the button escape. So I'm going to hit end mode here, and now I won't place more voltage sources when I click. But let's keep grabbing some components. So we're going to go back up to place, PSpice component, and we'll grab an inductor this time. This has the correct orientation, but if you need to change it, if you wanted to rotate it, I think it's just, I'm going to say it's Control R. Yeah, if you hold Control and R, or hold down Control and click R, it'll rotate the part for you. But like I said, by default, it's the way I like it, the way I find most pleasing to the eye. So I'm going to do that, and this time I'm going to hit Escape to end mode so I don't keep placing those inductors. Okay, next is the MOSFET. I need an N-channel MOSFET, so I'm going to come up to place again, PSpice component, and this time your MOSFETs and many other things, so BJTs, your NPN and PNP BJTs, your op amps, those things can be found under discrete, and those are usually that language kind of reflects what you can buy in real life. So like you can buy discrete or a single piece N MOSFET or a single piece op amp. Just discrete, it means like by itself. So I'm going to place down a power NMOS. I think you can get this to work with the NMOS, but I had a little bit of trouble with my simulations with that. So click on this power NMOS for this, and we're going to place that just somewhere around here. That should work just fine. And then again, I don't want to place any more of those, so I'm going to hit the escape key to get out of that. Alright. Next is the diode, so I'm going to hit place, PSpice component, diode, bring it down, and again, it's in the right orientation, but if it wasn't, I can hold down Control and hit R. That's going to rotate it for me. Place that there, hit escape to get out of that. Now I'm going to show you a different way to grab parts. Another way is to hit on your keyboard. You can hit the letter P to open up this parts menu over here on the right. I'm going to close that. I think you can also open that by going to place, part. You can click on this and open this up. This is pretty good. It allows you to search for, if you knew like the part number of whatever component you were trying to use, you can type that in here. I don't know, let's just say this 107 op amp. If I typed in 107, it automatically goes to that for me. And then if I double click it, oh, whoops, I accidentally clicked on the schematic too fast. So if I double click this, it's going to bring it in on my cursor, but I don't need that part, so I'm not going to use it. But if you know the name of the component, you can find it here. For the parts we're going to be using today, I need a capacitor, and I know off memory that if I just hit C, it gives me this C analog. What this means is it's a capacitor that's in the analog library. Down here is the list of all the libraries I've got loaded into this project. Unfortunately, I've messed around with my OrCad enough to where it's not going to be the exact same as whatever you get by default when you install, if you come in with a new install. So you might not have these libraries. So you can click this button to add a library, but you got to go search out on your computer to find it. And if you don't know what library that your part's in, it can make things really complicated. So I don't really recommend this place part menu for like a brand new person, because again, you have to know the name of the part, what library it's in. It kind of makes it difficult, but this is an option. If I know that if it's a C component in the analog library, I can just double click on that, and it brings in a capacitor for me. And that is not the correct orientation, so I can hit Control R. I'm going to rotate it around, make things look a little nicer. Hit escape to get out of placing capacitors. And the last thing I need is my load. And again, I'm not going to put a bunch of diodes down on this circuit because I want to keep it simple for this video. But I'm going to place a resistor, so I can either come up here and type R, and it'll find a resistor, notice the picture, in the analog library, or I can kill this menu, and I come up here to place PSpice component, resistor. We've seen that before. Another way to grab components though is to do search. You can click here and search for specific components, but I'm getting off track here. I'll do another video on the basics of OrCad, I think, but for now I'm just going to grab a resistor and place it down so we can get on with the circuit and the simulation. And so I again place down that resistor just so I have a load for my boost circuit to work on, and I'm gonna set it up so it draws about the same amount of current. Well, eventually I'll set it up so it draws about the same amount of current as the LEDs will. So next I'm gonna go up here. Sorry. I'm gonna put my grounds down now. To do that, you can either hit the G key on your keyboard and it'll bring up this menu, place ground. I always use this 0 symbol in the CapSim library, so if I click on that, it'll bring it down for me, and I can place those as I go. I'm going to leave this one, and another way to get to that is go place and then ground down here, and it'll bring up that same menu. You just got to look for the one you like. They have different symbols and things like that, but I like this CapSim one. So hit OK, come down here and just drop it somewhere, and hit escape to get out of that. So again, if you're new, I'd recommend going to this place menu and doing PSpice component for all the kind of passive and active components, and then this ground for your grounds. So now we got to wire all this up, and again, there's a couple ways to do that. If you get familiar, once you get familiar with the icons, you'll recognize this one as place wire. So I can click on that and come over here and click on the nodes and start connecting things up. And it's got this nice feature. I clicked on this once, and if I go up and then right, it'll automatically give me that corner, which is pretty handy. If I start clicking up here, I'm going to get wires, but I don't want that, so I'm going to hit escape to exit that mode, and it left me with that piece. So I'm going to select it with the left click and then just hit delete. Another way to place those wires is to go up to place again, and wires right here for you. So just click on the nodes, keep things going. Okay. Alright. And I right click there because I want to stop drawing wires, so end wire. Alright, now I'm going to change the value on some of these components. To do that, just go up to the components, like the description for its value, and double click on that, and it'll pull up this menu. So for the inductor, I'm going to change it to 50 millihenry. Hit enter. For the capacitor, I'm going to change that guy to 1 microfarad. Hit enter. The resistor, I'm going to leave at 1K, but this voltage source I'm going to change to, double click to open this, and then 3 volts DC. Hit enter. Alright, so if we compare that to what we've got drawn here, it's pretty much the same circuit. Granted, the LEDs are just changed to a resistor, but we're missing one part, and that's this pulse width modulation, the input to our NMOS transistor. To get that, we're going to be using a different voltage source. So I'll go back here and I'll place it for you guys. So the one we're going to be using is under place, PSpice component, and then source. I gotta let my dog out real quick. Hang on. Sorry about that. Voltage source, and then it's going to be this pulse voltage source. And that doesn't sound, well, it kind of does sound like pulse width modulation hop. So we're going to place that guy. And you'll click on that, it'll bring this down, and I'm going to place that. Now you're going to notice we have a whole bunch of things going on with this voltage source. If you want to zoom in on your schematic, hold the control key and then scroll your mouse wheel. Or you can do these zoom options up here, but I usually like to use my mouse. So I've got all these parameters that I need to set for this voltage source. To make things look prettier to my eye, I'm going to select all these by left clicking to drag a box, and then I'm going to just move these over here, get them out of the way. And to complete the circuit, I'm going to hit the G key to drop a ground, select the one I want, do OK, drop that there, and then I'm going to wire that guy in. So it's just a voltage source between ground and then the gate of that power MOSFET. Right click and then hit end wire. But now I need to set all these parameters for the pulse voltage source. So you'll notice we have V1, V2, TD, TR, TF, PW, and PER. So what are those things? Well, this was just a reminder. If you remember in the last video, we calculated to get 30 volts out from a 3 volt input, we need a duty cycle of 0.9 or 90%. But here is the voltage pulse breakdown. This is how I describe it, and it's pretty much it's just going to draw a periodic waveform of pulses, which is great because if you'll notice that looks an awful lot like our pulse width modulation. And these are the parameters that go into it, and that's V1, which is the initial voltage, which is the voltage level it starts off at. So that could either be 0 or you could set it to something else you want. V2 is the pulse voltage. That's the level it's going to go to when the pulse is on. TD is the time delay, and that's the amount of time before it starts drawing a periodic waveform or starts pulsing. So with this diagram, I tried to draw a kind of description of what these things are. So V1 is your initial voltage level. V2 is the voltage level that the pulses will occur at. TD is the amount of time right here before pulses start occurring. TR is the rise time, so that's the change in time between when the pulse starts. So right here at this corner to here, it takes this amount of time for it to rise from V1 volts to V2 volts, and so that TR parameter is this that width. I hope that makes sense. And TF is that same thing, but at the end when it falls back down to its initial voltage. These parameters are due to the fact that a lot of the times you will have some sort of time delay between when you have your voltage switch. Like nothing's perfect. You're never going to get a perfect square wave. Although if you look at it on an oscilloscope, a lot of the times it'll look pretty close to perfect, and that's because things are pretty dang good. But those things do exist in real life, so they wanted to give you an option to be able to model them. This PW is the pulse width, and that is the width of the pulse, and I think that includes the rise and fall times. So TR and TF, keep that in mind. And period is the period of the waveform. So depending on what frequency you're running it at or what you set it at, it's going to be this total length of time between however long the pulse occurs and then however long the pulse isn't there. Hopefully that makes sense. Let me check what I drew next. Oh, yeah. Okay, so we're going to set those now. We're going to start off at 0 volts because I don't want any pulses coming in. So just, double click on that V1 text to open this menu and then type in 0 volts and hit OK. On V2, now I'm going to have that go to 5 volts, so I'm going to type in 5 volts, hit enter. Double click TD, or my time delay. I'm going to put in now I gotta let the dog back in. Kurt! Alright, come on. Good boy. Get up there. Go ahead. Okay, professional video, right? Yeah, that's how it goes. So here's my time delay. I'm just gonna set that to 0 seconds. Oh no, I got another one coming. TR is my rise time. I want these pretty close to ideal. So on my rise time, I just usually put in 1 nanosecond. So type in 1 and then lowercase ns, nanoseconds. For my fall time, same thing, double click, 1 nanosecond, hit enter. For my pulse width, I'm going 9 microseconds. And then for the period, I'm going to put in 10 microseconds. So just to make that a little more obvious, what I've done here by setting the period to 10 microseconds is I've set the frequency of my waveform to the inverse of that, because your period is the inverse of your frequency. So if I have 10 microseconds, so 10 times 10 to the negative 6th, and I invert that, I'm going to get a frequency of about 100 kilohertz. And so by setting my the total period to 10 microseconds and the pulse width to 9 microseconds, what I've effectively done, is if my whole period is 10 microseconds and I set there's the other dog. You coming in? Alright, come on. I'm just gonna leave that open. Okay, so if I set the total period to 10 microseconds and the on time to 9 microseconds, I've given myself an on time of 90%, or my duty cycle is set to 90%, which is exactly what we want. And since the total period is 10 microseconds, my my end frequency is 100 kilohertz. Hopefully that makes sense. And then I want to zoom out, so I'm going to hold down Control, scroll back a little bit, and here we've got our circuit finished. So now we're going to work on simulating it, and to do that we need to create a simulation profile so it knows what kind of simulation we want to run, how long to run the simulation for, and even kind of what we want to look at in our circuit. So first thing I'm going to do is come up to this PSpice menu and hit New Simulation Profile. And for this I'm just going to type in trans, and that's short for transient, and I'm going to hit enter to create, and it's going to take a second, but it's going to pop up this simulation settings. Let me think, how long do I want to run this to? I'm going to run my simulation to 50 milliseconds, and I'm going to leave this in under the analysis type option. I'm going to leave it as transient. There's a few options here like bias point, DC sweep. I'm not going to get into those in this video, but what we're interested in is seeing if the output voltage becomes what we want, which is 30 volts, and how long it takes to get up to that, and maybe looking at some of the current and voltage waveforms as they occur. So I'm going to leave it in time domain transient because we want to observe how things change as time goes on. And I'm going to start saving data after 0. That's just fine. Actually, all these options are fine. So 50 milliseconds, and then I'm going to hit OK. So now I've got that simulation profile set up, and you can observe that if you go under PSpice resources over here on the left, you'll notice I have two simulation profiles. One is this bias option, or bias profile. That's set up for you automatically by default. And then the trans one is the one we just created. That one's going to be listed as red, and that is because it is it's the active simulation profile. That's why it turned red. If I wanted to change those later on, you just click on it and go to make active. But I created that one. We want to use that one. Yeah, okay. So now we're about ready to simulate. And to simulate, all you have to do once your simulation profile is set up is click this button up here. It says Run PSpice. I think you can also go to PSpice Run. But you can tell it what you want to look for before you run your simulation, and that just automatically pops it up on the waveform displayer automatically for you. And it's also, it kind of makes it handy if somebody else pulled up your design, they could see what you were trying to look at. So what we're obviously interested in is seeing this output voltage on our simulated load. So I'm going to go ahead and click this voltage level marker, and it's going to give me this probe attached to my cursor. And I come over here, and if I click on the node, the output node, it's going to place that probe marker. And my computer's running pretty slow, but it places that probe marker there. And that's the only one I'm really interested in. So I'm going to go ahead and right click and then end mode to get out of that. And now it's all set. So I'm going to click that Run PSpice button, and it's going to come down here, create a netlist, and it's going to pop up this other window, and that is our simulation window. And you'll notice it had to increment the time as it went on until it reached 100%. And what it means by 100% is it evaluated out, let me maximize this, until it got to that 50 milliseconds. If you remember, that's what we set in our simulation profile. We wanted it to run to 50 milliseconds. So what are we looking at on this? You'll notice that the time is the x-axis, and over here on the left it looks like we have voltage. And this is, again, since we set that output marker, over here, we wanted to observe the voltage on this node. And this is just like if you're attaching a multimeter to it physically, is what that probe's trying to indicate, which is kind of a cool feature of OrCad. But what we're observing is that node voltage. And you'll see as time goes on, it starts out around 3 volts, and then it slowly increases until we get up to around 30 volts. And so that was our objective, right? And so we should feel pretty dang proud of ourselves at this point. We'll notice that it looks a little bit thick up here, and if we zoom in, so if we use this zoom area button, you can zoom in, and we'll notice that there's a lot of ripple on that. If I zoom in even more on a skinnier section of time, you'll notice that the voltage, it shifts between, I don't know, 29.6 volts all the way down to 29.3 volts. So we've got about a 0.3 ripple voltage on the output, which may or may not be acceptable for what you're going to do. And in a later video, I'll show you how to tweak these things. If you want to zoom back out, hit the zoom fit button. But as far as the theory goes, yeah, we got exactly what we wanted. It's boosting that 3 volts up to 30 volts, and that's what our output's seeing, which is great. A few things I wanted to mention in this video were just that with this pretty simple circuit, that boost circuit, we got our output to 30 volts. But I also wanted to show, the inductor current relating to voltage output. So in order to do that, we're going to want to display 2 different things on our graph here. I'm not going to explain why I'm about to do this step, but I'm going to go into, plot, add y-axis, and then I'm going to go trace, add trace, and I want to view the inductor current, so that's IL1. Okay. I can show you why I just did that. Basically, what I did was I created another y-axis over here, which gave me a current axis, so it's going from 0 amps to 400 milliamps. If I would have placed them both on the same y-axis, the units would have went away, and I would have been looking at something that spans from 0 to 30 for my voltage, like putting that on the same graph as something that only spans from 0 to 0.3, and it really makes it hard to read the graphs as you go along. But I wanted to point out that our inductor current is always above 0 in this in the circuit we've drawn. It never comes down here. It's always above 0, and if we zoom in on it, so you can draw a box by just left click dragging, and then I think you can hit the zoom area button to zoom in on it. You'll notice that the inductor has some current ripple on it, and that comes from, oh man, was I supposed to go into, I think I talked about how, yeah, I did. I derived the basic theory behind the boost converter in the last video, and if you remember, we had to have what was called the continuous current mode. That's the mode we were using for our boost converter, and all the equations we derived were based on the assumption that the increase in inductor current when the inductor is being charged, so when the MOSFET's shorted, basically when the MOSFET's on, it is equal to the decrease in current in the inductor when the MOSFET's open, so off. And here it obviously is. We're up at a nice healthy, I don't know, 306.75, something like that. I don't know exactly, but something up there, and it never goes anywhere near down to 0. If you go into discontinuous current mode, your waveforms will not look anything like this. Your current will be much closer down to 0 amps, and it will even go into the negative numbers, and that's when you're going to get into discontinuous current. But one thing I did want to point out, so I'm going to zoom back in on the current. I'm going to come out here. Oh, you'll notice that for the first part of the graph, things are still changing quite a bit. I mean, everything's increasing, the current's increasing, voltage is increasing, but out here things kind of level off, and that's our steady state mode. So that's what we're interested in, because those are what our equations are based on. So I'm going to zoom in on this area here, and what we're looking at is the inductor current. To get a measurement, you can click on the graph and then do a right click and then cursor on, and it pops up this nice menu down here. I don't know if you can see this. Is there a better way to do this? I'll just stretch these out. Okay, so we've got the cursor. Now if when I left click on the map, or on the graph, the cursors are going to track things. So they're going to track the waveform, and it tells you what cursors are on what waveform. Since I have voltage and a current, I could place the cursors on either one, but fortunately for us, the cursor 1 and 2 is on current, which is what we're observing. So I'm going to put my current, or my first cursor, at the peak of this guy. Actually, let's see what we're looking at first. Sorry. Yeah, that's what I want to do. Okay, and then by using the right mouse button, I can move the other cursor. I'm going to put that at the very bottom. And what that's going to let me see is the change in current versus the change in time. And so from the graph, it looks like we're getting about, down here, see how it has y1 minus 2? We're getting a change in current of about 529 microamps. So remember that number. And that is occurring in, where's the time? Sorry, I forgot where it tells you the time. Oh, I think it's about 1 microsecond. Sorry, and that makes sense because if our duty cycle's 90% and it's 10 microseconds for the total period, then it's going to be off for 1 microsecond. So again, we're changing about 529 microamps in about 1 microsecond. So if we go back to our equation, you'll remember that the voltage on the inductor is equal to the inductance times the change in current divided by the change in time. So if we plugged in our numbers that we got from our graph back there, it's about 528 microamps divided by that 1 microsecond. And if we remember to look at our schematic, we had a 50 millihenry inductor. So going back, if you do this calculation, you'll get that the voltage on the inductor, so VL, is about 26.4 volts. And if you remember the original equation, since our circuit is the input voltage plus the inductor voltage, is going to give us roughly our output voltage. We have 3 volts for the input voltage plus 26.4 volts for the inductor voltage is going to equal 29.4 volts on the output. And from our graph, it is interesting to note that that is about where this thing sits at. Let me think. There were a few other things I wanted to talk about in this video, but I don't think I'll get into them, except for the fact that I think it's really cool to look at. Oh, whoops, sorry. Click on the zoom area button. If I zoom in on the voltage, I really like looking at this part when it's, sorry, I'll zoom back out. As the voltage is the green waveform. As it's getting charged up, it's going to, like, obviously it's charging. And so if I zoom in on that area, we get to see that it charges to a higher voltage, and then as it's draining, it comes down a little bit, but then it goes back up again and does that saw pattern, but it's slowly increasing. And I really like that because, again, for me, it ties back to the metaphor of like the girl pushing her dad on the swing. Each time she pushes with what she has, and slowly he goes higher and higher until she gets to where she wants him to be. So even though she's not that strong, she can get her dad up to 5 feet. Well, kind of similarly, even though I only have 3 volts, by leveraging the properties of the inductor, I'm able to use that 3 volts to slowly push things up, push by push by push, until I get it to 30 volts. And it levels off there due to several steady state conditions, again, those equations that we satisfied. But I think I'm going to stop the video here because I bet it's getting pretty long. But hopefully that's a good, simple overview on how to use OrCad to get a simulation. And the next video I'm going to be deriving this, well, I'm going to be showing you how to implement a simple circuit to give us our pulse width modulation and how to simulate that in OrCad too. So thanks for watching, and hopefully you enjoyed that.